mishaps apparently with the recording, and I'm sorry for those mishaps. I'm not sure why the last lecture wasn't recorded, but as you may have seen from my email, I went back to the videos from last year, and there's no one-to-one video that would exactly cover this lecture, but I gave you 2 videos, and I gave the times between which you start watching the first video after that time, and you stop watching the second one before that time. That's pretty much the material that I covered in our last lecture. And I got an email today from one of you that also something funny has happened with the exercise session videos, and Shobi is looking into that because we were under the impression that we posted a complete video, but one of you said that it's actually a significantly shorter version of what was actually said in the lecture. So we're looking into that. I just saw that message not long ago. Okay, so apparently the recording is running now. So I want to go back to where I left off last time. And the bigger theme that we've been discussing is understanding nonlinear dynamics near fixed points. And a prelude to that has been linear dynamics, because one thing, our first inclination is replace a nonlinear system with a linear one at a fixed point locally. So there was a brief review of linear systems theory, at least to the extent that it's relevant for what we're talking about here. And then we're working towards establishing under what conditions can I actually use the linearized phase portrait to make a conclusion about the nonlinear dynamics. This is still not global nonlinear dynamics, it's still just local, but there are questions to be answered there. So let me quickly stroll back to the context, and the context was here. So we're looking at a nonlinear dynamical system sufficiently smooth, and assume that we have a fixed point, all right? And when you have a fixed point, you can, as discussed many times, you can shift coordinates. And if the fixed point was at x0, you simply linearly shift coordinates, and the fixed point will be at y = 0 in the new coordinates. You then replace the system with its linearization, which simply amounts to taking the Jacobian at the original location and multiplying it by y, which is your deviation from the fixed point. Everything is general. Y is n-dimensional, and hence this Jacobian is represented by an n by n matrix. Okay, so what we hope is that we do get relevant information from this. In what sense? That, well, in the sense of course, a linear system is not the same as a nonlinear system, but that's not what we're fishing for. What we're fishing for is that, at least in a qualitative sense, we can get a good idea as to what happens near the origin. However, that's not a very precise statement in a qualitative sense. So how could we make that more rigorous? And the last lecture was about that. So for autonomous systems, there's a very powerful tool in dynamical systems that people have developed for saying that 2 types of dynamics are similar qualitatively. So if you have dynamical systems, system 1 and dynamical system 2, and they have flow maps f of t, g of t, mind you that these are autonomous dynamical systems, then we say that they are CK equivalent, and that CK equivalence is the most general notion of dynamically similar. So we say they are CK equivalent, where k is a natural number, on some open set. If, roughly speaking, on that open set you have a diffeomorphism, a CK diffeomorphism that maps the orbits into the orbit of one system into the orbits of the other system, preserving the orientation, but not necessarily the parametrization by time. And this was the relevant figure. This is the open set. Both systems are defined on that open set of Rn. And here's the flow, what the flow map does to one of the initial conditions for one of the systems. And the relationship between the 2 systems is that for each, and there exists a general CK diffeomorphism. That's the same CK that appears here in the statement of CK equivalent. Remember what a CK diffeomorphism is. It's a differentiable mapping, k times differentiable mapping with a k times differentiable inverse. So it's really a nice mapping in both directions, right? So there is one that just maps trajectories of one of the systems into the trajectories of the other systems. And mind you, it's the same mapping for all. So I'm not allowed to change the mapping as I go from one orbit to the other. So it really is a well-defined deformation of the orbit structure of one system by a given map into the orbit structure of the other system. Also, mind you that this diffeomorphism doesn't depend on time, so it works universally. It's really just a deformation of the domain, if you will. So you act on the domain, and after you have acted on the domain, what used to be the painted orbits of one of the dynamical systems are turned into the painted orbits of the other dynamical system. Okay, so that's the way to think about it. And if you have that, then what's required is that the evolution direction should be the same on those, the orientation, but the way time is ticking is not necessarily the same along them. So I just said that when k equals 0, you get the weakest possible form of CK equivalence, which is C0 equivalence. And that is a special name, topological equivalence. When you say topological typically in dynamical systems, it means that it's a relationship which is the weakest possible, because it doesn't insist on any kind of differentiability. It just means continuity, and that's the case here. And if we also aspire for mappings between two dynamical systems for which we don't even have to adjust the time, and we manage to find one, then that's clearly a stronger notion of equivalence, right? Then we just say that the two systems are CK conjugate, like here. So then the time that appears here is the same. So that means that first, this was the CK equivalence definition. Basically, you take an initial condition, general X, you act, or you deform it, and then you act on that with the flow map of the second system. And for all initial conditions, that should be exactly the same as first, acting on that initial condition with the flow map of the first system, and then applying the domain deformation. In other words, going from this point first to this initial condition, then moving forward should fully commute with the other operation of first flowing this initial condition here and moving forward. Okay, and there should be an H, and that's the big deal. I could certainly do that for any two pieces of curves, but there is a time-independent H, which is the same for any initial condition. So it's really just a domain deformation. It's domain-dependent rather than trajectory-dependent. So we looked at examples of topologically equivalent linear systems. So first of all, this is not our end result. This is not where we're heading. We want relationships between linear and nonlinear systems, but just to test this notion, what are equivalent systems under this topological equivalence? We looked at linear systems, and nothing prevents you to use this construct between linear systems, because these were completely general dynamical systems here, right? So, not that I proved this, but I was relying in your intuition that if you have a stable focus, then and you have a stable sink, then perhaps more intuitively, you can go with a continuous deformation from the sink to the focus just by simply grabbing this ordered structure and twisting it, just rotate it, right? So a rotation with shear that leaves the midpoint fixed. Now, with a rotation like that, everything is continuous, but you will have a differentiability issue right here, okay? But when you perform that, it's still, also you can undo it, which means it's invertible. So these are, therefore, the expectation is that these two phase portraits are topologically equivalent because they are CK equivalent with k equals 0, and that turns out to be the case. There's also the stable node, which also you can imagine the deformation going from here just by, starting to deform these in a consistent fashion and say leave two of these curves undeformed, but then start pushing the other curves maybe closer to one of them. But of course, you will have infinitely many curves, so it's not that they will get arbitrarily close to this, because you need to do this in a continuous fashion. So something like that, and then you end up getting the stable node. So these are all topologically equivalent, and you could say, well, do I really want to call these in some sense equivalent with each other? Because they don't really look equivalent to each other. They have distinctly different phase portraits. And the answer to that is yes, they have differences, but from a practical perspective, which is very often, is the equilibrium point stable or not? If it's stable, is it asymptotically stable or not? From that perspective, these are identical because you end up at the origin no matter what, right? In some case, in the first case, you oscillate a little bit, but fundamentally, your fate is determined. Here, you had on completely straight lines at the same rate. Here, you're also heading towards the equilibrium point. There is some differentiation in the rates because if you go here, you go faster. If you slower, if you go here, you go faster. And here, the general one will be a combination of these. So there are details of the dynamics that are different, no question. But from the point of view of stability, they are equivalent. That's the statement. And what makes them equivalent, if you look at it, is that the number of the eigenvalues used with negative real parts is the same. Okay. And then we pretty much covered anything that's possible in 2D. So what's not topologically equivalent is, for instance, a stable spiral and a non-stable spiral, much as we would like to say, oh, two spirals, they are equivalent, right? I mean, spiral. Well, I in fact get the other one from the second one from the other one. I just change these arrows. The problem with that is that it doesn't preserve the orientation, right? Because here, this initial condition, that initial condition approach each other in forward time. So their image under the homeomorphism, if it's a homeomorphism, should also approach the two image points because homeomorphism means continuous, but that's not happening here, right? This point is here fixed, and the image point, as time goes by, is going away. So there cannot be a homeomorphism that does this along orbits and keeps the orientation. That's not going to happen. And this is then another reason, the saddle, the argument against these being topologically conjugate is again not that this has straight lines going through these points, whereas this has, lines that are spiral. That's not a continuous mapping can deal with that. That's not the issue. If in fact, if I turn these arrows in this direction, then this would already be topologically equivalent to the other one. The issue is the orientation, because again, whereas some of the points obey orientation, preservation, others don't, because these two initial conditions are moving away from each other, right? Well, this one stays, but the other one moves away, so the distance between the two grows, whereas here all distances shrink. So these cannot be then topologically equivalent. Just a brief word about this sort of mysterious thing of why do I distinguish the C0 case from the rest? It seems like arbitrary. Why don't I have a special name for things up to C1 or C3? Why C0 is the one that deserves a special name? It turns out that you can check it very easily, that the minute you allow for even just C1 or C2, these two, let's just go back, these guys would no longer be equivalent. So that would be a much sharper notion of equivalence than these. So the C0 is general enough to allow for this kind of, so it's optimal from the point of view of stability. If when C1, immediately, not the case. You would have to have a much closer relationship. And in fact, you can see what that relationship, if you go back here, I didn't say it at the time, let's just actually worry about CK conjugacy, but I could do the same thing on CK on CK equivalence. So let's just make a note here. So if K, this degree of smoothness for the conjugacy, is larger than equal to 1, seems like what's the big deal now? It's 0 or 1 or 2 or 7. It's a major difference when it's not 0 anymore, but 1, because the minute it's 1, I can differentiate this defining relationship at least once. Okay, I can work with it very directly using the tools of calculus. So then do a d by dx. So apply d by dx, which is it's a Jacobian operation to let's just call this star. And this is no black magic. You can do this calculation by the chain rule, right? So you go like dH, and then by the chain rule, you will have to take the Jacobian of the flow map. I'm differentiating with respect to f of t, with respect to the argument, the innermost argument, which is x. And then I do this on the other side. So dgt, these are then just matrices when you compute them in coordinates. And I should be consistent and use the same sign. Okay, dH. So these are now linear mappings. And say I evaluate them at a given point, and that could be at an equilibrium point, for instance, say the two fixed points. When I do that, then the linearized flow map, you might remember, is in fact e to the at, where a would be the coefficient matrix of the linearization. So one of the systems, and for the other one, it would be e to the bt, because those are the linearized systems for 1 and 2. So at a fixed point, this amounts to dH, say e to the at, and it's equal to e to the bt dH. And I don't have that much room left, but hopefully you can now, the H, don't forget it's a CK diffeomorphism. So when you differentiate, its Jacobian will have an inverse. So you can multiply both sides of this equation by the inverse. Maybe that much I need. So I push this a little bit further to the left, to the right. But then I start moving other things, right? So I shouldn't be grabbing the F from the if, sorry. Try to be more careful here. Okay, so I move this here, okay? And then the implication from this is e to the at, which is the fundamental solution matrix of one of the differential equations linearized, say at x equals 0. Well, let's just assume that these are the linear system, so the two equilibria both are at 0. That would be dH inverse e to the bt. I don't have that much room, but hopefully I have just enough dH. So what does that tell you? It tells you that this matrix, which makes the solutions of the linearized equation of the first differential equation go forward in time, and the other one, which does that for the second differential equation, they are by definition what we call similar matrices, or I think this, yeah, this is the definition of similar. And if they are similar matrices, just a fact from linear algebra is that the eigenvalues have to be the same. So that's a very strict constraint. It really then would not allow for any slack. It would really require, where's it would certainly not allow these to be called equivalent. Sometimes you don't want, you want that distinction. But for the general purpose of just kind of what's the qualitative nature of the dynamics, those details are minute. And certainly you don't want to insist that they have the exact same eigenvalues, right? So just that kind of innocent looking change from 0 to 1 immediately imposes a major restriction just at this linear level already, right? So the thing to remember is that if I have enough room, maybe I just say that in words, that this is a very strict relationship, very strict equivalence between the two systems. And that's why we don't tend to use that, because we generally, that would be just too restrictive. And I want to be a whole lot more cavalier in terms of relating or pronouncing systems equivalent to each other. Any questions so far before I move to hyperbolic points?
Yes, I have a quick question. Can you hear me?
Yeah.
Yeah, in example 8,
I just have to increase your volume, sorry.
it's okay.
But
In example 8, in the saddle, so the figure to the right, you mentioned that if the direction on the diagonals would be inverted so that they're all directed towards the center, the saddle would be topologically equivalent to the stable spiral.
not to the to the stable, sorry, yes.
Yes,
but I made there's a typo there if that's what you're referring to. This is an unstable spiral.
Yeah, but aren't there trajectories that are approaching the fixed point and then moving away in the saddle?
You're right. What I said was not correct, because I was just what I meant to say is that if thank you, that was inaccurate what I said. If these two were like this, then that by itself would not eliminate a relationship between the two. So if I only pay attention to these two lines, then I would not have such an easy counterexample to the conjugacy. But you're absolutely right, Ahmed, that when I start looking at the other trajectories, then clearly I have a problem, because the other initial conditions here would approach this trajectory for all times. Hence, their image under already a homeomorphism would also have to approach each other. Now, there's temporary approach for a while, but after that, it goes away. So thank you. That's correct. I was too much focusing on these two lines. Yeah.
Thank you.
Thank you. Anybody else? I did start talking about hyperbolic fixed points. Hyperbolicity is a major concept in dynamical systems as people are searching for robust objects, things that you want to worry about. We don't want to worry about things that are non-generic and non-observable and everything. So modern theory of dynamical systems is very focused on physically relevant, observable phenomena. And as you will see, that brings us to the notion of fixed points that are hyperbolic. And we'll see that what this means, even though the term itself hyperbolic, it doesn't convey that meaning, but what that means in dynamical systems in general, something robust. And that notion extends from fixed points to general sets, as I may have mentioned. You can talk about hyperbolic periodic orbits, hyperbolic attractors, anything which basically has a certain degree of robustness, meaning that if you perturb the system, then whatever you had, of course, will move and deform and change somewhat, but will persist. There will be a nearby object of the same type, which is what you want, because you always have parameter uncertainties in systems, right? So if you make a very specific conclusion about the fixed point, you sort of understand that if you change the system, that might move, but not more. So it should move if the uncertainty is small, but it should also remain of the same kind, say in terms of stability. So how can you ensure that? So for fixed points, it turns out to be that the right notion of that robustness is hyperbolicity, which means that, as I said, the definition of that would be, is that you have a dynamical, nonlinear dynamical system like that, then if all eigen, and this is a fixed point for that, then if all eigenvalues of the Jacobian, which is the coefficient matrix of the linearization, satisfy this simple inequality, meaning that the real part is non-zero, then you have a hyperbolic fixed point. And this is really easy to remember. It's even easier to remember, perhaps, through a picture. So when you look at the linearization or at a fixed point of your dynamical system, then you look at the eigenvalues. So this would be the real part of all eigenvalues of the linearization. This is the imaginary part of all the eigenvalues. Okay, so the lambda I goes from 1 to n, are together they form what we could say the spectrum of dfx naught, but let's just say again, eigenvalues of dfx naught. And remember, Justin knows the reason why we're talking about that Jacobian is that the linearization of the dynamical system at the fixed point, at x naught, I should say, is this system y dot equals df x naught y. And this is a constant coefficient linear autonomous differential equation. This is a constant. Therefore, the solution matrix of this fundamental is e to the at, where this is a. And the eigenvalues of a are related to the eigenvalues of e to the t, so a to the at. So the eigenvalues of this matrix that you see here do have a decisive influence on the local stability type. But it's not so much about the particular stability type, but the robustness of stability. So for a hyperbolic fixed point, the kind of eigenvalue configuration you should see is that you may have an eigenvalue here, and you may have a complex conjugate of that there. You may have, several eigenvalues here, some of which might be actually even repeated multiple times. And you can have the same on the other side. Lots of eigenvalues with negative real parts. You can have complex conjugates, simple or repeated. But one thing you cannot have eigenvalues right on the imaginary axis. So this axis is off limits. You cannot have anything there. So that's the thing to remember. That's the only restriction. And any fixed point that satisfies this is hyperbolic. So no eigenvalues here. So it's not so much about stability, because stability is determined by the sign of the real part, and we're allowing for both, but you cannot have it here. So before we kind of see the implications of that, there's one observation that I'd like to make, which tells you, and this is fairly straightforward to see, but brings in some tools that we use in this class. So observe that the linearized stability of a fixed point, of a hyperbolic fixed point, is preserved under perturbation. So hyperbolic fixed points, I should write it like this. Hyperbolic fixed points and their stability type persists under small perturbations. So it's robust. You could say, well, it's very restrictive. Why small perturbations? How small? And so on. We don't know. That will be system specific, but it would be unrealistic to hope that if you give a huge perturbation to a dynamical system, then everything will also remain the same. That's unrealistic. That's not going to happen. Then you're really changing it to a completely different system, right? What we want is that, hey, I have a reasonable model. Okay, I have a reasonable understanding of the system. Not complete, but reasonable. So I'm fairly close to reality. The difference between my model and reality is small. Can I still then claim that whatever conclusion I get from my model is also there in reality with some small perturbations, okay, and which we all understand. I mean, it's like when an experimentalist shows an error bar, right? All the conclusions. It's precisely the rigorous mathematical definition of that, giving you essentially, I don't know the thickness of the error bar. That's the only difference. Normally, it's in the order of the perturbation that I allow to the system, but there's a multiplication there that I don't know, but it's of the same order. But there is an error bar. So that's the kind of the fit statement that we're looking for. And I'll just give you a proof, because this is not hard to see. And again, it brings in ideas that are relevant otherwise. So if you want a small perturbation of a dynamical system, which is x dot equals f of x. Let's just keep it autonomous for now. So a small perturbation of that, we generally write it in the following form: x dot equals f of x. And the famous epsilon in mathematics, gx, and epsilon is always small in mathematics, that to the extent, in fact, that I was invited once to a dinner which was only attended by mathematicians, and this was one of the big jokes at the table. And the joke just went like this: let's consider epsilon less than 0. And everybody was laughing because epsilon is always bigger than 0 or equal to 0. if you don't find that funny, you're not alone. I also didn't. I mean, I knew what they meant, but would this be the highlight of the evening? I didn't think so. Anyway, so but epsilon is in this setting certainly. Actually, you know what? Let's just be unorthodox and allow epsilon to be negative, but it's certainly much less than 1. So in norm, it can either be 0. So that's what a small perturbation is to a dynamical system. And mind you, it's not just a small perturbation to a particular parameter. We're actually allowing for everything here, unmodeled nonlinearities, things that we don't think are important, but at the end of the day, they potentially have the power to upset our conclusions that we gather from here. So this is what a small perturbation looks like. And the first question that's actually that we need to address, if you give this one a careful reading, hyperbolic fixed points and their stability type persists. So the first thing we have to actually address is that hyperbolic fixed points persist, which, is that clear? Is that obvious? That if I perturb a system and it had a fixed point, then the new system also has a fixed point? It's very important, obviously. Right? Because if it doesn't, then why invest in the analysis of that fixed point to begin with? So what are the conditions for that? So the first question is, does the perturbed system have a nearby fixed point? The best I can hope for is nearby, but for that I do hope for. So what does that mean? Well, I can check, right? Because if that nearby fixed point is x epsilon, then what I'm hoping for is that when I now look for fixed points after perturbation, excuse me, then it would satisfy this equation. But does it have? Do we have a solution? And it should be nearby. Okay. And here, the reason why I'm mentioning this is because it's clearly a fundamental question. And what really helps here is the implicit function theorem. Don't know about you, but when I learned the implicit function theorem first in a math class, it was a complete puzzle to me why that would be helpful. And certainly there were no real life examples. This is a real life example. It's whenever you invest in analyzing the fixed point of any model that you ever work with in applied science and engineering, this question will come up. And the basic tool to answer that turns out to be the implicit function theorem, because the implicit function theorem is all about the solvability of equations of the type, this particular form. I mean, it's a lot more general than that. So you have fx epsilon equals 0, and that's a question whether you can solve that. It's a function that depends on x and also some parameter epsilon, and the question is whether you can solve that. But you do know that for epsilon equals 0, you do have a solution, and that solution is the fixed point that you have been looking at, right? Why can I write it in that abstract form? Because just look at this form here, right? So this will be this whole thing here will be fx epsilon, the right-hand side of the perturbed equation. And I know that if I set epsilon equal to 0, then this term is out and I'm down to f of x. And for that, I have assumed that f of the x naught is a fixed point. So we have assumed, which I haven't written here, that f of x naught is equal to 0. So x naught is a fixed point. That's our standing. There's our starting point, right? So this is certainly given. And then the question is, can I use the existence of that fixed point to say something about the existence of a fixed point here, which means can I continue the solution of this equation in epsilon? And the implicit function theorem says that yes, if It's not automatic. But if you then check the Jacobian of your capital F with respect to the variable x at criticality, okay, and you find that this is non-singular, so at epsilon equals 0. And you find that F, that same equation that you're trying to solve, is at least continuously differentiable with respect to epsilon, then the answer is positive. So under these conditions, there exists, in fact, a unique nearby solution to the equation that you're trying to solve. So there exists an x epsilon, which is x naught plus, and here comes the nearby. It's order epsilon. So I don't know exactly what that is quantitatively, but it certainly vanishes if I put epsilon, if I make epsilon go to 0. And even if I divide this quantity by epsilon and take the limit of epsilon going to 0, that's the meaning of big O, then I get a finite limit. Okay. So that's an orderly transition to 0. A nearby solution to the equation to fx epsilon equals 0. Well, if I have a nearby solution to the equation, it means that I have a nearby fixed point. Now, I was too quick to make this check. These are the assumptions. Now I need to, that's just the implicit function theorem, but I need to check if this is really true. Now the first line is true, these assumptions, because I did find, this was my starting point, that I had an equilibrium, right? But I have to check if this derivative is non-singular. So what does that mean? It means that I have to take the x derivative of what I see here and then plug in x naught, x equals x naught, and epsilon equals 0. That's what this condition says, right? So when you do that, then you will have the gradient of this f here, and you will have the gradient of g. But when you set epsilon equal to 0, this term will actually be out. So what really matters here is the Jacobian of f. So note, in our current context, this Jacobian that is so crucial in terms of the continuation of your fixed point is just df x naught, right? Now, is it non-singular? Well, it's actually more than non-singular, because I have made an assumption that if that x naught is hyperbolic, because I'm making this statement about hyperbolic fixed points here. So hyperbolic fixed points. So if x naught was hyperbolic, then it had an eigenvalue configuration like this. And among other things, since it cannot have any eigenvalues here, it can certainly have no 0 eigenvalue. So that's an implication. I'm actually, when I say the equilibrium is hyperbolic, I actually require more than needed for its persistence, because when it's hyperbolic, you cannot have eigenvalues here either. But for the point of view of the persistence of the equilibrium, that would be actually still allowed. However, this axis certainly contains a 0, and I'm fine because I'm not allowing any eigenvalues anywhere here. So in particular, I cannot have any at 0. So this is then is non-singular by the hyperbolicity of x naught. So x naught persists as a nearby x epsilon equals x naught plus order epsilon. And the smaller the perturbation, the closer that persisting fixed point is. And I will just make here that remarked, this is now remark number 2, that x naught also survives if it is non-hyperbolic as long as d fx naught has no zero eigenvalue. So that means that you could also have a center, for instance, whose eigenvalues are here. It doesn't turn out to be terribly robust in terms of its stability, as we'll talk about it in a second, but it certainly persists as a nearby fixed point. Okay, so for instance, they persist as fixed points. I'm not saying they persist as centers, because that's another question, whether the stability type also persists. And that's what I'm going to look at next, because we just addressed the first question here, which was where? Which was here, fixed point. Okay, so let's move on to the second question. And the second question was, does the persisting fixed point have the same stability type? Because that's the claim. And the answer turns out to be positive, and for the following reason. Well, I can check that, right? Because I simply go ahead and linearize again along the persisting fixed point, right? So my linearized system now, again, the variable y is now x minus x epsilon, right? And then I need to take the right-hand side, which is now the perturbed right-hand side. So it includes what I had initially plus the perturbation. Okay, I need to take that Jacobian, and then I have to plug in x epsilon, which, mind you, is x naught plus order epsilon times epsilon. This is the new linearized dynamical system at the new equilibrium point. Okay, but that's not that hard to do. Just imagine I can just jump the parentheses with the differentiation sign, and I have to take d of f. Okay, and then once I have taken the d of f, now I plug in x naught plus order epsilon. So what this means is that I have taken that derivative and I plug in x naught plus order epsilon, and I jump epsilon with the d because it's a spatial differentiation. I take the derivative of g and I plug in x naught plus order epsilon. And then f and g are smooth enough. I assume that at least they're C1, so that I have reasonable existence. They do have to be smooth for this argument. Well, yeah, I mean, it's easier. Let's just assume at least they're once continuously differentiable. I don't want to stay in the Lipschitz category, although I think that this would be doable there as well. But anyway, C1, then you can Taylor expand them and just keep the first order terms. So df at x naught, and I'm Taylor expanding with respect to epsilon. So this is the epsilon equals 0 term, and everything else is order epsilon. Okay. It just so happens that in the other term here, already everything, the lowest order term is epsilon, right? So I don't even have to Taylor expand that. So I have dfx naught plus order epsilon. And that is the perturbed coefficient matrix. So what I have here is A plus order epsilon. Okay. So when I go ahead and the A was the, did I say what that was here? Yeah, earlier. So if I now go ahead and calculate the characteristic equation for this, because I'm interested in the eigenvalues of the new linearization, then what's the characteristic equation? Is determinant of, A, let's call this A epsilon minus lambda I equals 0. So what I will be doing, I will be calculating the coefficients of this characteristic equation. So basically, I'm getting a new polynomial whose coefficients are small perturbations of the original coefficients. Now that I can just, you either believe that or look this up, that there is a theorem in algebra, which is very believable. It says that if you have a polynomial whose roots or whose coefficients are continuous functions of a parameter, then the eigenvalues of the roots of that polynomial, which are the eigenvalues in this case, will be also continuous functions of that parameters, which is very believable, right? If you make small changes to the roots of a polynomial, then they will be moving by a small amount. In fact, if you make smooth changes, they also move smoothly, not just continuously, as long as they are not repeated. Because repeated eigenvalues, when you have collapse of eigenvalues, going this way and then move that way. So the smoothness is not immediate, but we don't need that. Continuous dependence is enough. So the thing what I'm using here is roots of polynomials are C0 functions of their coefficients. And the coefficients here since they are small perturbations of the coefficients of the original A characteristic polynomial. So those coefficients are C0 in epsilon in this case. So at the end of the day, if you make a small change in epsilon, then the roots of the polynomial will change by an order epsilon amount. So if I now go again to the complex plane, and I take stock of what I have, so these are the real parts, these are the imaginary parts. And remember now, again, it's going to be crucial that I have a hyperbolic fixed point. So that line is off limits. So the possible eigenvalue configurations are still pretty rich, but they have to stay away from that line. So all this. And yes, I can have some repeated eigenvalues as well. But when I circle these crosses, it means that they're repeated. And they can split into, so this is what when you see one cross here, it's actually two crosses in that case, okay, or three crosses. So this can in fact split, and part of the eigenvalues may go in this direction, in which case these will go in this direction, one of those directions, right? So say this way, and the remaining eigenvalue, which was at the same spot, might be just going this way. So this is possible, right? And so that then there are two routes here crossing each other, so there's no smoothness anymore. But certainly, if the change in the coefficients of the polynomial is small, then the splitting will not get you far either. So it's going to be localized. So for that reason, the way to show this kind of pictorially is that when you then start tinkering with epsilon, then they will all be, those that are repeated might be splitting, but they all will be moving in order epsilon little balls. So these are size of order epsilon balls. Ball just means that the terminology is that I mean not the circle itself, but the interior. And then it just remains to observe that if I then keep epsilon small enough, then I can make these balls arbitrarily small. So even if I was super close here, with this one, or even closer with this pair to that red line, I still had a finite distance, some distance, maybe 10 to the minus 17, but it was a distance. And now I can keep epsilon small enough, it's within my control, then I will be smaller even than that distance. But it also shows you, right, the issue. So let me just make the conclusion. For small enough epsilon norm, the eigenvalues remain bounded away from the real part lambda I equals 0 line. So that means that x epsilon is hyperbolic. And you kind of see two things that, yes, but the weakest link here in the chain, which is whoever the closest is, will tell me how small I need to keep epsilon. Because as I grow epsilon, after a while, all bets are off. The small enough argument doesn't work because these, after a while, may easily hit the imaginary axis. If they hit the imaginary axis, then I'm no longer hyperbolic. Okay. But it also tells you the significance of hyperbolicity. This argument I could not make for centers, but I can make for hyperbolic fixed points precisely because I stayed away from the imaginary axis. If I had a center type fixed point, it would still survive by the implicit function theorem. But for the center type fixed point, I would have then eigenvalues here. And then when I apply a small perturbation on that, when I look at the linearization and that surviving fixed point, everything here goes through without change, except my final, my final conclusion, I would have to worry about small perturbations of these. And, I would have no idea how exactly they move. They might move to the left, they might move to the right. And the actual stability type as a result changed, the engine stability type as a result of that perturbation is anybody's guess, right? We're highly dependent on a given system, right? That's why we like hyperbolic fixed points. And that's why it seemed like we're asking too much when we were talking about persistence of the fixed point itself. But now you perhaps see that if you want more than that, if you also want persistence of stability, you do need more than just no zero eigenvalues. You need hyperbolicity precisely. Because if you violate just with one eigenvalue your hyperbolicity, then any small uncertainty or anything, that epsilon term that you don't even know. You don't even know what you don't know, right? Because that's why you kind of didn't include it in your model to begin with. That might get you here or that might get you there. And that's a completely different game, the two sides, right? So that's the, so I'll just say that in words that note non-hyperbolic fixed points. Fixed points may persist as fixed points, centers, but their stability type may change. You may be very lucky in some cases, and then you perturb these eigenvalues, and just so happens that, they actually move along this line. And then your stability type didn't change. And that's, in fact, what happens in conservative systems. There are constraints that keep them here, because if you have a single eigenvalue here, then if this moves here, then the other one has to move here too, and this would actually include, if there's nothing that balances that, then this would induce decay in the system, say down to the equilibrium point. You would be losing energy. And that type of, there are individual systems in which you're prevented you are prevented from happening. But then let me even then step back and really ask the question that, are there real conservative systems in real life? There are really conservative fully? No, because even when you hit the pendulum, after a while, it will come to a stop, right? So in the most general sense, you have to allow for all types of small perturbations, no matter how small they are. And then in that case, nothing is conservative anymore. So these constraints are not there anymore. So that's why we don't like those types of systems for practical conclusions. So, and again, the reason was this, that you can just leave the axis and you either go in the regime of growing oscillations or decaying oscillations. Any questions? I made a note myself just in my notes that there was also a question, so why do we call these fixed points hyperbolic? Where's the term coming from? And to the best of my knowledge, it comes from the single example. So the prototype fixed point, if you want, or to many of us, the absolute robust fixed point, not robust, all are robust, but sort of the most general example is the saddle point. So as a hyperbolic fixed point. So why? Because the saddle point conveys the fact, when I use it as an example, that it's not so much the stability I worry about, because this is not stable. So in certain directions, you go to the origin, and in other directions, you go away from the origin. So ultimately, this is unstable. And yet, I worry about, yet I like the saddle point because it's persistent in its nature. So, and due to its hyperbolicity. So if you get saddle under linearization, then you can bet that even under the uncertainties and modeling assumptions, there will be a nearby saddle. So it's not stable. So it's not so much the stability, but the stability type, okay? And then I think the association is that we call these are hyperbole in the idealized case. And that's why people then sort of think of this as a hyperbolic fixed point. You might say it's a misnomer because this is also a hyperbolic fixed point and there's no hyperbole here. And you're absolutely right. This is just one of those conventional things that somebody fixed this terminology. So this is a hyperbolic fixed point. This is a hyperbolic fixed point. This is a hyperbolic fixed point too. Okay, so nobody says that all hyperbolic fixed points are topologically equivalent to each other. Why? Because they may well have eigenvalue configurations on different sides of this, or the saddle has one here and one there. It's not about the stability type. It's about the robustness of your conclusions about it. So in terms of, this is a good thing to have in your model. In terms of robustness, this is a good thing to have in your model in terms of robustness. So let's look at one of the simplest models, again, the pendulum, just to see how these things work out when you actually compute them. So this would be, I think, example 9, according to my notes. And as usual, the pendulum, stability of fixed points in the pendulum. And just to sort of fix these ideas on the simplest possible case. Okay, so I'm not going to draw it again. We've seen this a few times. So the original equation is phi double dot for the angle of the pendulum, right? Plus sine phi equals 0. And the first thing we do, to do the analysis in a dynamical system sense, we typically bring this to a first order form. So x1 dot equals x2. It's a non-dimensionalized pendulum because normally you would have a g over L here, but g being the gravity, L being the length, we take those to be 1. So x1 dot equals x2 and x2 dot equals minus sine x1. Okay. And the phase space variable is x1, x2. And if I just go by the book, okay, then I will say, all right, so the simplest things that I can do, this is a nonlinear system, assume that I don't know what it does. As the first thing I do, I look for fixed points, okay, and then try to take it from there. And in this case, I can find them by hand, but you would do in a general case, you would ask a solver, a Newton-Raphson solver, you would give the right-hand side to that solver, and it would, if it works well, it returns the zeros of the right-hand side, maybe with some help, because the iteration will depend on the initial condition that you give to the solver. But I assume that's doable. But in this case, you would not rely on that, because you know that there's a fixed point, say the upper equilibrium. Let's call it P, which is pi for the position and 0 for the velocity. Okay, so suppose this happens to be this fixed point of the pendulum, right? Because phi is the position, so pi is up there and it's not moving, so the velocity is 0. Okay. Now I can make this transpose so that to be consistent with the fact that I wrote this as a column vector, so then this should also be a column vector, right? So when I don't know what I'm going to get yet, unlike here, then I just go by the book, as I said. So you look at the linearization. At P. So you take the Jacobian of the right-hand side. There will be a two-dimensional y variable, which is the measure of your deviation from that equilibrium point. It's multiplied by A. That's the coefficient matrix, which is the Jacobian evaluated at that point, y. So let's be more specific in this case. A is the Jacobian, which is sort of the right-hand side, right? The two-dimensional function taken at this point P. So how do you evaluate that? Let's actually bring this a little bit closer here. Okay, so what you need to do is calculate the Jacobian. So you go to the first line. This is here. Sorry. What you see here is f of x. It's a vector valued function depending on two-dimensional vector mapping into R2. And the Jacobian is such that you take the first row of this function and you first differentiate with respect to x1, which is 0, because there's no dependence on x1. And when you differentiate with respect to x2, you get a 1. So in the second row, when you differentiate with respect to x1, the derivative sign is cosine, so you get minus cosine x1. And no dependence on x2, so you get 0 here. And you need to evaluate this at the point P. And P, remember, is pi and 0. Okay. So for x1, you plug in pi. For x2, you plug in 0, but there's no dependence on the latter. So you basically just end up getting 0, 1. So the cosine x1, the cosine of pi is -1, but minus minus is plus. So this is what you get. The eigenvalues of this, you get by checking the characteristic equation, A minus lambda I. I trust you can do that. Calculate the eigenvalues of this matrix. And what you end up getting is lambda 1 equals, and label the first one -1, and lambda 2 is +1. So these are the eigenvalues. Before I go any further, I can immediately celebrate that I have invested my time correctly on this on this fixed point, because this is something that will survive small perturbations. So if my model for the pendulum was somewhat inaccurate, and there are little things unevenness, then little air resistance, little this and that, still, if those are small, then I will still have something nearby of the same stability type. Excuse me. And the reason for that conclusion is that these eigenvalues are off the imaginary axis, right? The complex plane, when I have real part of lambda I and imaginary part of lambda I, then these eigenvalues are here and there. Okay, so what I have is a hyperbolic fixed point. So no question that it will persist. But I can ask further questions. What does it exactly look like? So what is the nature of the solution of this linear system here? beyond the fact that it's going to be robust, whatever it is. So the next step for that, in order to build the solutions, you need to calculate also the eigenvectors corresponding to these eigenvalues, right? So again, I trust you can do that. So the one corresponding to the lambda one, which is the negative eigenvalue, that turns out to be -1, 1. And the other one, S2, corresponding to lambda 2 equals +1, will be 1, 1. Okay. So therefore, based on that, the linearized dynamics, if I actually want to have a picture, the linearized dynamics is, in order for me to do a picture, I'm also doing this partly to kind of review the review that we did on linear systems. This is one of the easier cases because the eigenvalues are not repeated. You take some constant times e to the first eigenvalue, which is -t, and you multiply that by the first eigenvector, which is S1. So -1, 1. Plus C2 times you take e to the exponential of the second eigenvalue times t. And remember, the second eigenvalue is here. So that's just going to be e to the +1 times t, e to the t. And you multiply that with the corresponding eigenvector. This is the way we build solutions. And this is the simplest case in which the eigenvalues are not repeated. And a way to rewrite this would be more in the advection or flow map form, is that since this is a linear system, it has a fundamental matrix solution which acts on the normalized fundamental matrix solution, which acts on the initial condition, and that gives you the current position. So from this one, you can rewrite, if all goes well, this is e to the -t, minus e to the -t, e to the -t, and then e to the t, e to the t here, and that matrix acting on the initial condition should be the same. So y10, y20. This is another way of writing this. Okay, I calculated the normalized fundamental matrix. So sorry, solution. Sorry. The normalized fundamental matrix solution, which would be here. And this is the initial condition. This is a different formulation here. These coefficients are just general coefficients. But if you take an initial value problem, so you say that y at time equals 0 should be this initial condition, and you solve that by setting this to 0 and 0, so then these become 1 and 1, and that should be equal to y10, y20. Then you get two equations for the unknowns C1 and C2. So I've already solved that, and I plug those then in, and then I rearrange what I get, because those will be then functions of y10 and y20, and this is what I should be getting. Okay. And so this is then the initial condition. And what you see here is e to the at, so the linearized flow map. It's also the same as taking the general nonlinear flow map, as I said, taking its derivative and plugging in the equilibrium point, TFTP. Okay, that's the same as e to the at. Okay, so just a different way of looking at it. So based on this, the linearized phase portrait is on two axes, y1 and y2. Again, these are locally defined coordinates, right? Remember the meaning of those. The y, did I say what they were? So here, I didn't say what they were, but y was x minus p, and p was this. Now, when I say linearized coordinates, I don't mean that they're only locally defined or local coordinates. Certainly, this relationship is defined everywhere, but when I analyze this system, the linearized system, it will only have an established relationship with the nonlinear system near x or equals y equals 0, okay, not globally. How do I know it will have a relationship? Because of hyperbolicity. Except, did I say that? So now I realize I haven't. I'm already showing an example for a theorem that I haven't stated. Please excuse me, which I got too much carried away. So basically, just now I realized that there's a missing statement here when I make this claim, and the missing statement is actually quite simple, but that's a powerful theorem that was a celebrated theorem when it was proved. Is the Hartman-Grobman theorem. The Hartman-Grobman theorem just says the following very simple but very powerful, not simple to prove, but simple to remember result. And it basically says, if you have a hyperbolic fixed point, then near the hyperbolic fixed point, the linearization is topologically equivalent to the nonlinear system. Okay, so it's as good as it gets, right? Except that I forgot to state that. So let me just squeeze that in, because actually I'll be using that here. Now, how do I do that? I think if I do this and I say plus, and I say current template, yeah, I was able to squeeze this in. Please, I'll come back to this in a second, okay? But I need to state this because that's what we were heading towards. So the theorem, which goes by the name of Hartman and Grobman, it's really a basic, not basic, but classic result. And it says that if the fixed point x naught of a dynamical system x dot equals f of x, autonomous at this point. There are complications when this system constantly changes in time, the right-hand side, then it's usually you don't even have fixed points anymore, by the way. That's atypical that you would have fixed points that really don't move, right? So let's just state this for autonomous systems. So if the fixed point pt, fixed point x naught of x dot equals fx, and this is general and dimensional, let's just assume that, you know, it's at least once continuously differentiable, is hyperbolic, then let's call this star, then the nonlinear system star is topologically equivalent . Remember, that means that it's a C0 equivalent to its linearization in fact, I now have to use the same variable because I imagine now that the linearization is defined on the same, I use just the same variables. However, then wait a second, let's just then shift the equilibrium point to 0, okay? It plays no role, but then I can use then y is equal to x, and I can always do this. I can always shift any equilibrium a priori, right, to 0. And that enables me just to write the linearization like this, okay? So it's linearization in a neighborhood, on an open neighborhood. Of x not equals 0. And that's a very powerful conclusion, because it means that if you find a hyperbolic fixed point, so you do a linearization, and this is what you find, that the eigenvalue configuration like this, then at some point you immediately have a guaranteed result for the nonlinear system, namely what you see in terms of the stability type is from the linear system is what you get for the nonlinear system, okay? You don't have to investigate that. What it doesn't say is that a linear system whose phase portrait, of course, I can draw endlessly and arbitrarily on large domains. It's not true that over the whole of Rn, that linear phase portrait will be relevant for the nonlinear system. No, it may well happen, and it does happen a lot, that it's only some small open neighborhood in which the nonlinear system can be deformed by a continuous, by homeomorphism into the linear system, right? But there is such a neighborhood. That's the point. You can only guarantee that in general if the fixed point is hyperbolic. Another thing to note is that this theorem, although it's very important and it's just really powerful, and you can basically sleep much better with this theorem, it still doesn't distinguish among these. So just based on this theorem, just based on this, it could happen that your linearization is this and your actual nonlinear dynamics is that. Why? Because these are in fact topologically equivalent. Okay, so just based on Hartman-Grobman, for all we know at this point, the details of the dynamics could change. So it's not powerful enough to guarantee more. We would certainly like to have more, right? You certainly would say that, wait a second, if my linearization tells me that this is a focus, then I'd rather have a focus also in the nonlinear problem, right? But much as we like this theorem, much as it is powerful, it doesn't guarantee that. So why? Because it doesn't really assume anything else. If you just assume a bit more, in fact, you can guarantee is that what you compute from the linearization in terms of detailed stability type, say a focus, and your nonlinear system will also have a focus, okay? But for that, you need to assume a little bit more, and the machinery then changes more. So what are the types of things you need to assume? I just sketched that here very quickly. So note, for all we know, so just based on Hartman-Grobman, okay, let me just be specific, a focus under linearization could turn into a node under the nonlinear terms. And the other way around. So, but if we assume further, so not only is the equilibrium point hyperbolic, but if we also assume, so I should say also, non-resonance conditions among the eigenvalues and you could say, well, what is that? There's no forcing here. What would be the resonance? And I don't even know if there are imaginary parts of the eigenvalues, right? That's where I don't even know if there are oscillations. And when we hear oscillations, when we hear resonance, we typically think of oscillations. But for all I know, my fixed point may have these eigenvalues, which are purely real. I may just have two of those. I may just have one of those, right? So what do I mean by a resonance or non-resonance? And it just means that the eigenvalues, when I take integer linear combinations of these, and I use k, I guess, for that. So if I take ki lambda I, then I should not be hitting lambda j. So here I goes from 1 to n, which n is the total number of eigenvalues, but I is not equal to j and k, because if I was equal to j, then I could just take, you know, the trivial linear combination ki would be equal to 1, which kj would be 1, right? And then 1 times lambda j equals lambda j. That would always violate this condition. Okay. So generally speaking, this is k bigger than or equal to 2, turns out. So if you have these, if you have them unconditionally for all k, then it turns out that you can even have an analytic mapping between the linear system and the full nonlinear system. But even in just a CK mapping between the two, remember that when you don't just think topological conjugacy, but you also start thinking C1 conjugacy, C2, the Hartman-Grobman doesn't guarantee C1 and C2. It only guarantees topological, which means that I can't do my favorite trick of differentiating any relationship, right? But the minute, remember my little remark here, the minute I can differentiate things, then I go ahead and differentiate them. Where was that remark? Here. And I basically did that here. So this is the CK equivalence relationship that I can just, I literally did it right at fixed points, right? Because that's how I was able to substitute this deformation gradient and gradient of format with e to the at. So I'm doing this right at fixed points. So I anticipated the discussion that I actually completely forgot, but now I'm making it. So remember our conclusion that in that case, when you can guarantee C1, already C1 conjugacy would work. I have an incredibly strong relationship between the two players. Even their eigenvalues have to be the same. So basically, if you have a linearization, a linear dynamical system, and you try to relate it to a nonlinear dynamical system, they are only C1 conjugates if the nonlinear dynamical system, when you linearize it, also has the same eigenvalues. And when you have this so strong constraint that the eigenvalues have to be equal as well, then you can no longer have clearly that one of the dynamical systems is a focus and the other one is a node, because it's a different eigenvalue configuration, right? So this is the reason why, if you require a little bit more, then you're able to ensure that not only do you have a topological relationship, a topological conjugacy, but a C1, or it's generally CK conjugacy here. Now, it's a little bit unfortunate that I'm using K for two different things. Let me actually make this capital K, okay? And capital K is a vector. So it's what it is, it's integer numbers. It's an n-dimensional vector of integer numbers that I use to take linear combinations of the eigenvalues. And with those linear combinations, I'm trying to hit other eigenvalues, always one that I had left out from here. So if we assume that these non-resonance conditions hold, then one can in fact, and they say, I think it goes like this, that, what is it? So R. So up to some integer R, then there is in fact, there exists a CR conjugacy. Between the linear system and nonlinear systems, still just locally. But that can be arbitrarily large. And then when the minute you have that strong a conjugacy, not just topological one, then even details of the stability type are preserved. And this is, in fact, the work of Sternberg. This is Sternberg's theorem. And it goes, and I think you can find it in some of the references that I've given to you, sort of in Ciccone. And note that R is in this, so R is the integer up to which these nonlinear combinations, these resonance relationships, non-resonance relationships remain satisfied. So suppose I check this and I find that for all integer vectors whose norm, what's the norm? It's not the Euclidean one, but it's simply K norm equals the sum of the Ki's, I going from 1 to n. So if I find that that norm, I can take, any integer vector up to, in norm up to R, but not higher than at least up to R, I can guarantee a conjugacy between the two systems. That's already pretty powerful, okay? But that R is therefore taken in general, what's allowed in this theorem, in various versions of that theorem, that can be the set of natural numbers, 1, 2, 3, 4, 5, but it can also be just infinity, the symbol infinity. So in fact, I'm not struggling with to say, because I never assumed as much differentiability. Oh, let's just say infinity. So the reason why I'm struggling is that if I cannot get more differentiable, relationships than the original system was here. So I would have to change this to CR as well. Let me do that. It didn't cost me anything here. Okay. So that's the original differentiability of the system. But when I originally defined the differentiability of the system here, it can even be analytic, which means that this has a convergent Taylor expansion. And I really wanted to say that this theorem has an analytic extension. So if this non-resonance relationship holds for all R's, so you can take it up to infinity symbolically, and the right-hand side was analytic, so it had a convergent Taylor series expansion, then you can, in fact, have an analytic linearization result, which means that there's an analytic transformation. So, C infinity, invertible, with convergent power series in both directions, that would transform your nonlinear system locally into a linear system. So there is, in fact, a change of coordinates, which is perfectly well defined. And even you can look for it in the form of a Taylor expansion that takes locally your nonlinear system and fully, without any residual, transforms it into a linear system. However, very important, this is only true. You can only go this far if you assume a lot about the eigenvalues, that there's no combination that would take you that would cause these resonance relationships. Okay. So this, I just say, also extends to analytical linearization. Because sometimes people just say R is symbolically allowed to be equal to A. So that was also a celebrated result, but I'm just listing this here because people often forget this. So generally speaking, just because you have a nonlinear system, and it's a hyperbolic fixed point, what you can say, it survives, it's persistent, and its stability type in terms of stable or unstable will not change. However, the details of it might change. If you assume more, that there's no resonant combination of these eigenvalues, then you get more. Just some insight, when you actually try to construct that transformation as a Taylor series, you really just say, you know what, I have a linear system. I'm blindly applying a change of coordinates that I don't know yet. And I look for it in the form of a Taylor expansion. I apply it. I calculate the differential equation in the new set of coordinates. When do I succeed with this? When can I build a transformation that transforms my system to linear? What the objective of that transformation would be is that in the transformed system, all the nonlinear terms vanish, okay? And you have the ability to make that happen because your Taylor coefficients are unknown, and you could select them in a way such that in the transformed system, they will vanish. Now, you can only solve those equations, make them vanish. It turns out that they will be actually solvable equations recursively if these conditions are satisfied. Because these guys, linear combination of this minus lambda j, will be appearing in your polynomial's denominators that you construct formally. And if this happens to be 0, then those coefficients blow up and you can't solve that equation that I have just described. Okay, so it's a very constructive way. Let's just actually try to linearize the system. Let's just throw in a Taylor expansion. Let's try to do it. And it turns out that if those will be precisely the denominators, these linear combinations minus lambda j that arise there. And if one of them is 0, the whole construct blows up. So this is very practical how this comes in. Okay, so what I will do then tomorrow is come back to this. My apologies for actually forgetting the main result, because this example 9 is meant to be an illustration of everything up, including this theorem. And I got away with just starting the illustration. But at this point, I wanted to make the point that what you get from the linearization is what you see for the nonlinear system, at least in terms of stability type. And that's when I realized I never stated that. So this is where I stopped today, and tomorrow we'll continue with this example, which is then also an illustration of the Hartman-Grobman theorem. Any questions? One question is, did I record the lecture this time? And for all I know, it has been recorded. So if there's no questions, okay, then have a good evening and see you tomorrow.